96% of the land area in Egypt consists of harsh, arid desert, a geographic reality that has restricted 95 million people to a narrow corridor along the Nile for several thousand years. Why has this ancient nation remained confined to such a small fraction of its territory for so long? The sheer scale of the Sahara creates a natural barrier that has historically proven impossible to overcome with traditional infrastructure. But this isolation is ending as Egypt executes a feat of engineering that no modern nation has ever attempted before. The construction of a massive man-made river is currently cutting through the burning desert sands. Tens of millions of liters of water are extracted from the Nile and propelled through a network of giant pumping stations. One can notice how the water is forced upward against gravity before it enters vast concrete canals. These channels are engineered with such immense width that they visually resemble natural rivers flowing through the dunes. But this is just the beginning. It only looks obvious to move water through a channel, but in reality, this infrastructure must traverse over 45 kilometers of scorching desert terrain to reach its destination. The goal is to provide irrigation to soil that has never been farmed in the history of the region. The process is only gaining momentum. The camera glides along the smooth concrete walls where the water maintains a steady velocity, preventing stagnation or evaporation losses in the extreme heat. Engineering plans for the new Delta River required precise calculations to ensure the water reached the harshest environments on Earth. Excavators move earth by the ton as the bed of the artificial river is lined with specialized materials. It is visible how the heavy machinery operates in high-temperature zones to lay the foundation for this agricultural expansion. Everything only gets more complicated when considering the hydraulic pressure required to keep the flow consistent over such vast distances. Automated systems and massive turbines work ceaselessly at the primary pumping stations to maintain the flow rate. Each station serves as a critical node, ensuring that the water reaches the new fields where life is being established. The transition to the next level of national development depends entirely on the stability of these concrete arteries. This complex system marks a significant shift in how the desert landscape is utilized for food security. From here, the newly reclaimed land begins its transformation as the water finally reaches the planned agricultural zones. The project concludes this phase of movement, opening the road to a future of expanded cultivation across the desert. 110 million people inhabit the modern Egyptian state, representing a demographic density that creates immense pressure on the nation's limited resources. Why does such a vast territory struggle to accommodate its citizens comfortably? At first glance, the map of Egypt appears expansive, but in reality, almost the entire population is concentrated within a narrow corridor along the Nile River. This fertile strip constitutes less than 5% of the total land area, while the remaining 95% is dominated by the inhospitable expanse of the Sahara Desert. The population continues to expand at a rapid pace. Arable land becomes dangerously scarce as urban centers consume the once productive soil of the original delta. One can notice how the boundaries between the green riverbanks and the arid wasteland are sharp and unforgiving. This environmental limitation forces a critical technical question. How can the hydraulic engineers of the 21st century transport the life-giving waters of the Nile across hundreds of kilometers of burning sand to foster new agricultural zones? $10 billion is the staggering investment the Egyptian government committed in the year 2021 to solve this crisis. The New Delta project represents an engineering endeavor of unprecedented scale and complexity. It involves the construction of hundreds of kilometers of artificial canals and sophisticated water infrastructure designed to bypass natural geography. The camera glides along the massive concrete foundations of the Hamam pumping station, a facility designed to move millions of cubic meters of water daily. It gets more complex further on. A primary distribution artery stretches over 170 kilometers across the desert floor, cutting through dunes that have remained dry for millennia. Secondary distribution channels branch out from the main canal like a circulatory system. High-capacity underground pipelines and massive reservoirs ensure that water is stored and distributed with minimal evaporation loss. One can notice the installation of a smart water management system where sensors and satellite monitoring equipment track flow rates in real time. But this is just the beginning. The objective extends beyond simple irrigation. The project aims to redistribute the population of 110 million people and secure long-term food stability. By pushing life deep into the white sands of the Sahara, the government seeks to establish a completely new delta region. The process is only gaining momentum as the first kilometers of desert are transformed into productive agricultural soil. The transformation of the desert landscape proceeds with methodical precision. Thus, the foundation is laid for a strategic expansion that will redefine the country's habitable geography for decades to come. 2021 marked the official commencement of the new Delta project, signaling the start of construction on an artificial river stretching 114 kilometers in length. This massive waterway was engineered to transport water from the lower reaches of the Nile River directly across the expanse of the arid desert. Why was such an immense mobilization of resources required for this specific desert corridor? The sheer scale of the engineering task necessitated the Egyptian government to deploy over 12,000 workers and hundreds of heavy-duty trucks, excavators, and bulldozers. This vast fleet operated without interruption across the scorched landscape. Long convoys of heavy machinery stretched toward the horizon, maintaining a schedule that ran 24 hours a day and 7 days a week. At first glance, the operation looked like a chaotic surge of steel, but in reality, the entire construction zone functioned as a synchronized mobile megawork site. Every refueling point, transportation route, and maintenance bay was coordinated with mathematical precision. But this is just the beginning. One can notice how hundreds of bulldozers moved in formation to level shifting sand dunes and cut down high ridges to redistribute the earth into lower basins. The primary objective was the creation of a flat, stable surface capable of supporting thousands of tons of heavy machinery without the risk of ground subsidence. Each segment underwent grading under the direct supervision of survey engineers who checked elevations and slopes to ensure total uniformity across the desert. The process is only gaining momentum. High-capacity conveyor systems moved excess sand away from the active work zone, while heavy compactors compressed the surface layer to form a reliable foundation. After a period of more than 2 months, once the sandy terrain had reached the required stability, hundreds of excavators and trucks began the specialized task of shaping the artificial riverbed itself. One can notice the formation of a wide U-shaped cross-section with a channel bottom measuring approximately 150 feet in width. The average depth reached 23 feet, a dimension calculated to allow water to flow naturally by gravity. Why was the depth and width so strictly maintained throughout the route? While it looks like a simple ditch, the geometry ensures the water moves without the need for energy-intensive pumping systems. Every single day, approximately 70,000 tons of sand and soil were extracted from the desert along a construction corridor extending nearly 250 miles. More than 1,200 engineers and operators worked in rotating shifts, enduring environmental conditions where temperatures frequently exceeded 115 degrees Fahrenheit. The longitudinal slope was controlled with a precision of just 1 inch for every 100 feet of distance. It gets more complex further on. Survey teams utilized laser leveling equipment every 160 feet to verify that the riverbed remained straight and aligned with the original design. Most of the excavated material was reused to construct lateral embankments, creating protective levees between 10 and 16 feet in height. One can notice how bulldozers cut through elevated ground layer by layer, while trucks delivered reinforcement material to lower zones. In areas characterized by weak soil, engineers drilled sand piles with a diameter of 16 inches to depths of 20 to 25 feet. The ground was further stabilized by mixing cement and clay into the substrate to prevent any future structural settling. Under the constant glare of the sun and through thick clouds of desert dust, the convoys of machinery moved in a continuous loop. Everything only gets more complicated as the earthworks phase transitioned into the lining stage. At first glance, digging the channel was the hardest part, but in reality, the desert sand poses a constant threat by rapidly absorbing and draining away any liquid. Consequently, the waterproofing and lining phase became the most critical technical challenge of the new Delta project. Workers first moistened and leveled the riverbed before applying a fine sand layer exactly 2 inches thick to serve as a bedding course. The equipment gradually laid 4 to 5 inch thick concrete slabs in sections measuring 16 feet by 10 feet. Expansion joints were integrated between every segment and sealed with hot bitumen to accommodate the extreme thermal expansion caused by desert temperature swings. In zones with particularly unstable ground, an additional high-density polyethylene waterproof membrane was installed beneath the concrete. This membrane was anchored with steel pins and protected by a sand cover to ensure long-term durability. 124 kilometers of the artificial river were ultimately lined with concrete, creating one of the largest waterproofing systems in North Africa. Along the banks, engineers planted vetiver grass and other drought-resistant vegetation to stabilize the slopes and block wind-blown sand from entering the channel. From an aerial perspective, the completed river now resembles a bright silver ribbon cutting through the vast sea of golden sand. Thus, the material structure of the waterway is finalized and prepared for the next phase of the regional transformation. 2 hectares is the exact surface area covered by each intermediate regulating reservoir constructed once the main canal bed reached its final stabilized elevation. Why is the creation of these massive basins necessary after the excavation of the primary channel? The flow of water from the main canal carries immense kinetic energy and fluctuations that could damage the entire infrastructure. By installing these reservoirs, engineers create a critical hydraulic buffer that slows the movement and allows for precise control of the water volume. Excavation of the raw ground occurs in strategic layers to form the wide basin and its gentle side slopes. This specific geometry is required to maintain ground stability within the unpredictable sandy desert conditions while maximizing the total storage capacity. The scale of these structures is significant, as each 2-hectare area is roughly equivalent to nearly 3 standard football fields. But this is just the beginning. The entire reservoir bottom undergoes a rigorous compaction process to create a solid foundation. One can notice how heavy machinery traverses the basin until the soil reaches the required density. It only looks obvious to move to the next stage, but in reality, the integrity of the desert floor depends on this compression. A waterproof lining consisting of high-density polyethylene or bitumen is then applied across the surface to prevent seepage and subsequent ground settlement. The process is only gaining momentum. Large concrete panels are either lowered into place by cranes or cast directly onto the waterproof lining. These panels form a durable, load-bearing surface that can withstand the mechanical forces of flowing water and resist long-term erosion. The camera glides along the grid of stone and cement, where every single joint is carefully sealed. Such precision ensures that the reservoir can operate reliably for many decades without leakage. Next, the construction of the inlet and outlet control structures begins. These mechanical units allow for the precise regulation of water levels and the even distribution of flow into the downstream pipelines or secondary canals. It is visible how the metal gates and sensors are integrated into the concrete walls of the basin. Everything only gets more complicated as the final reinforcement of the surrounding embankment slopes takes place. Workers finish the outer edges to protect the structural integrity of the reservoir against the elements. Through these combined technical steps, the regulating reservoir becomes a permanent hydraulic shield for the downstream water conveyance system. The transformation moves to the next phase of processing as the water management network nears completion. 150 millimeters, exactly the thickness of the dense reinforcement steel that forms the structural skeleton of the water control weir. Why is such a massive metal frame required before a single drop of concrete is poured? At first glance, the desert sand seems like an unstable foundation for a heavy hydraulic structure, but in reality, the reinforcement distributes the load across the entire base to prevent shifting. This skeleton ensures that the massive concrete body above can withstand the relentless pressure of the diverted flow. Construction began with deep foundation excavation and shaping of the base to the exact design elevation. Engineers meticulously prepared the earth to ensure sufficient load-bearing capacity within the sandy desert soils. Dense reinforcement steel was installed in segmented bays, creating a rigid grid of metal. One can notice how the dark steel bars intersect at right angles, forming a cage that defines the dimensions of the weir. The process is only gaining momentum. Scaffolding and formwork were then fully assembled, allowing for the precise shaping of large concrete walls, beams, and slabs. Concrete was poured continuously using long-reach pump booms that extend dozens of meters into the air. One can notice the gray mixture flowing steadily into the forms, where it is evenly layered to create a monolithic structure and minimize construction joints. The equipment gradually fills every void of the reinforcement grid. Throughout the pouring process, elevation and surface flatness were closely monitored. This prevents future water flow from causing localized erosion through turbulence. Once the concrete reached the required strength, the formwork was removed, revealing the completed concrete control structure. It gets more complex further on. Installation of the water regulating connections at each discharge bay followed the curing of the gated control dam. Large diameter steel pipe sections were precisely lifted into position by heavy cranes. They were aligned coaxially with the openings that had been preformed within the concrete structure. The pipe flanges were pressed against embedded steel base plates. High-strength bolts were then used to secure the components, ensuring long-term stability and watertight performance. Engineering teams carefully controlled and balanced the clamping force around the entire circumference during bolt tightening. This specific action prevents misalignment and localized stress on the metal. The joints were then inspected for sealing integrity, elevation accuracy, and flow direction. It does not end at this stage. At the water distribution outlet, large steel pipe sections were installed in sequence from the dam structure. These components form parallel conveyance lines extending downstream across the landscape. Inside the pipeline, joints were either fully welded or flange bolted in accordance with engineering standards. Each pipe segment was lowered into place by a crane, with its elevation and alignment carefully adjusted. One can notice the slow, methodical movement of the manipulators as they set the steel in place. After all connections were completed, the entire pipeline alignment was checked for coaxial accuracy. The interior was cleaned to remove any residual materials before the system was commissioned. The regulating dam was then fully prepared for integration with the downstream gate system and water distribution network. The flow of construction moves toward the final connection without haste. 1,500 millimeters is the minimum diameter for the steel branch lines that carry water deep into the desert agricultural zones. Why construct parallel pipelines instead of traditional open canals? The open water surface would lead to massive evaporation in the arid climate. By utilizing closed steel conduits, the project ensures an independent distribution network where each branch functions as a self-contained system. Large-scale excavation crews prepare the terrain by carving long, parallel trenches into the ground with high-precision uniform depth. The equipment gradually removes thousands of cubic meters of sand to ensure the pipelines rest at a specific design elevation. This allows the massive volume of water to move entirely by gravity, eliminating the need for constant mechanical propulsion. It seems simple to lay a pipe, but in reality, a deviation of even a few centimeters would disrupt the hydraulic pressure of the entire branch. Prefabricated steel modules, each reaching lengths of tens of meters, are organized in group staging areas. Heavy-duty cranes maneuver these massive cylinders, lowering them sequentially into the prepared trenches. One can notice how the pipe sections are suspended in the air before being placed onto supports. The process is only gaining momentum. Specialized teams use elevation measuring instruments to align each module along a common axis before any connection is made. This precision prevents operational stress and structural misalignment that could lead to ruptures under the weight of the water. Automated welding systems then execute full circumference arc welding, creating continuous 360-degree seams. These welds act as a permanent seal against the immense internal pressure of the flow. Is the structural integrity of the joint guaranteed by the weld alone? Only through rigorous testing can the engineers be certain. Each connection point undergoes ultrasonic testing or pressure leak checks to identify microscopic gaps or defects. It is visible how sensors scan the metal for any inconsistency that might cause future leakage deep underground. Everything only gets more complicated as the assembly concludes. Workers enter the interior to remove welding slag and residual construction materials, ensuring the inner surface is perfectly smooth. Fine sand is then poured around the pipe in a controlled manner, forming a protective bedding layer. This granular cushion distributes external loads and prevents the steel from deforming due to uneven settlement of the desert floor. Backfilling occurs in measured layers, with compaction equipment securing the pipelines against the harsh conditions of the shifting terrain. But this is just the beginning of the infrastructure. At the upstream end, near the banks of the Nile River, an intelligent pumping station serves as the heart of the network. High-capacity submersible pump units are positioned within reinforced concrete intake basins to maintain a stable flow regardless of river level fluctuations. One can notice the massive intake pipes reaching deep into the water source. These units are managed by variable frequency drives, or VFDs, which are integrated into a central electrical control system. This technology allows for real-time adjustments of pump speeds based on the actual demand of the downstream agricultural sectors. Water level and pressure sensors continuously transmit digital data to the automated control hub. At first glance, the station appears to be a standard industrial facility, but in reality, it optimizes energy efficiency by calculating the exact power needed for every liter of water moved. Transition to the next level occurs as the construction phase ends. After years of labor across the desert expanse, the gates are opened for the first time. Nile water surges into the newly completed network of canals and steel pipelines. The flow fills regulating reservoirs and passes through control structures with a calculated steady pace. Engineers monitor every segment during this initial opening to verify that the hydraulic pressure remains within safe parameters. The water advances deep into the parallel branch systems, turning the theoretical designs of the blueprints into a functional reality. The liquid moves through the pipes, reaching the distant agricultural zones to begin its intended purpose. Thus, the massive engineering project transitions into its operational phase, securing a stable flow across the landscape. 200,000 hectares of newly reclaimed territory are currently taking shape on what was once a completely barren and empty desert landscape. Why did these specific green circles suddenly appear in the middle of the arid wasteland? It would seem that the sand is incapable of supporting life, but the arrival of the artificial river has changed the local physics of the soil. The water delivered through this massive conveyance network has reached these coordinates, breathing life into agricultural zones that did not exist only a short time ago. On land that was previously void of any vegetation, massive center pivot irrigation systems rise from the ground. One can notice how these mechanical structures rotate slowly around a fixed central point, moving with the steady pace of giant clock hands turning across the desert expanse. With each controlled rotation, the water is evenly absorbed into the parched soil, transitioning hot sand into productive farmland that can now be cultivated 365 days a year. From a high altitude, these perfect circles represent more than the simple geometry of modern engineering. They serve as visible proof that the desert is being redefined into a functional resource. The process is only gaining momentum. Expanding the total area of productive land strengthens food security and reshapes the entire future of the region by creating a stable resource base. Alongside the development of crop farming, industrial livestock production was initiated simultaneously on the newly reclaimed territories. What were once shifting sand plots underwent a rigorous engineering transformation. The ground was leveled, the soil structure was stabilized, and the area was subdivided into precise sectors. Only after this preparation were prefabricated steel frames erected in strictly coordinated phases. It is visible how the equipment gradually assembles these structures into a unified industrial complex. In a remarkably short period, large-scale livestock barns took shape on the former desert surface, featuring heavy roof structures, reinforced structural columns, and solid concrete floors. These massive operations were designed according to a rigorous industrial model, with each individual complex capable of housing up to 6,000 cattle within a single integrated system. The open barn configuration utilizes natural ventilation and specialized sun shading, which allows the herds to adapt to the high temperatures of the arid climate. At first glance, the system seems isolated, but in reality, it is fully integrated into the regional water infrastructure. Water from the main conveyance network is branched specifically for livestock requirements, providing a continuous supply for drinking, sanitation, and evaporative cooling. Everything only gets more complicated as the cycles of the farm begin to interconnect. Feed for the cattle is produced directly from the surrounding newly cultivated fields, creating a closed-loop system that links crop production and animal husbandry into one efficient chain. One can notice how the proximity of the fields minimizes the logistics of nutrient transfer between the two sectors. Beef from these specialized farms is delivered directly into the domestic supply chain. This strategic output reduces the national reliance on international imports and ensures a stable, predictable food supply for the entire domestic market. The transformation moves from the open desert into a structured industrial cycle without haste. Tens of billions of dollars is the estimated capital expenditure invested into the construction of this artificial waterway designed to redirect resources from the Nile. Why would a nation commit such a staggering sum to a single engineering endeavor? This project serves as the primary structural foundation for the massive New Delta initiative, which has required nearly one full decade of continuous construction. But this is just the beginning. It seems simple to view this as a mere irrigation canal, but in reality, the scale of the financial investment is secondary to the long-term strategic value the infrastructure provides for the entire region. One can notice how the landscape transitions from arid dunes into a structured network of channels and pumping stations. The equipment gradually reshapes the topography of the Sahara, turning barren ground into a complex industrial and agricultural ecosystem. It is visible how the water moves through the newly carved channels, supporting a chain that includes land reclamation, crop cultivation, and livestock management. Everything only gets more complicated as the project expands. Therefore, the transformation extends beyond hydraulic engineering to include entire food supply chains and logistics networks. The process is only gaining momentum. This reshaped desert represents a total overhaul of the national infrastructure, ensuring food security through modern irrigation technology. From here, the transformation moves to the next phase of processing as the new ecosystem begins to function. The project concludes this phase, opening the road to further agricultural formation. Thus ends the detailed overview of the technical construction of the artificial river.